Hey everyone, welcome back. And today we will be doing another lead code problem 559, maximum depth of an array tree. An easy one. Given an array tree, find its maximum depth. The maximum depth is the number of nodes along the longest path from root node down to the furthest leaf node. The N-ary input serialization is represented in their level order traversal. So this is just a level order traversal, and yes, it is a level order traversal. And each group of children is represented by the null value. See the examples. Yes, this is a level order traversal. Yes. So what they want us to do is, first of all, we have given an array tree. So this is not a binary tree. Whenever we have a binary tree, the node can have two children, but this is an n-ary tree, which means the node can have more than two children in that tree. So we will be taking the example too, because this is just more easy, not easy, but this by taking this we will be understanding things more easier. So here you can see, like, a node can have four children, more than four, or whatever the case is. But if it was a binary tree, for example, if there was not a four node, like this four node was not here, then this would have been a binary tree, because there would have been two and no more than two nodes uh, having the same child, having the same parent. Yes, yes, they have the same parent. Yes, okay, this is good now. So what they want us to do is just return the maximum depth of an n-ary tree. We have already done the binary tree depth, which was an easy one, because we just go to the left, go to the right, check what is the maximum and just return it, and that was easy. But in this problem we have to do it on an array tree. So here you can see the maximum depth is going to be 1 3 7 11 14. So this is how we can just see and tell things. So what we can do is to solve this problem by two methods, obviously, like the breadth first search and the depth first search. So the breadth first search will be just going level by level. So each level we will have our level incremented. So that's how the breadth first search works. And breadth first search usually is applied when we want to go left to right. So this is how we want to do things in our level order traversal. Like, if you know how what a level order traversal is, eh, just going level by level and appending the nodes in our input, uh, not in our input, in our list. And now we can just use the breadth first search to find the maximum height. What was it, height or the depth? Maximum depth. Yes, so that's it. And otherwise, if you do not want to do this by breadth first search, breadth first search is much easier though. But if you do not want to do this by breadth first search, what we can do is just apply depth first search, which is just going to the farthest, you can say, leaf node, and coming back again and going down again, and coming back again and going down. For example, one will hit two, and then three, and then three will go down to six, and the maximum at that point is being updated. So 1 2 3 7 11 14. This is how we can get the maximum, and now we can go further, but the maximum is not going to be updated. But what we are doing is traversing to every node, so it is a linear time solution and of n. So that's it. So let's get started. First of all, we will be doing the depth first search. Let me just comment it down, like, okay. So this is the depth first search solution in which, so how do we use depth first search? We know that we make a stack, append it to our stack. If there is a root to begin with, we will just append it to our stack dot append it with a tuple. So a tuple will be having a root and alongside the level. So the root have the level 1, so we'll be taking this example. Root has the level 1, and now what we'll be doing is taking the depth, which will be our resultant, which we are going to return. You can see, while there is something in the stack, we will say, if there is something in the stack, we just want to remove that tuple, basically pop that tuple. So how we are going to do this, just stack dot pop, and after popping it, we can just put the node in node, uh, yes, the node in node, and the level in level. And now what we'll be doing is, increasing our depth or checking our depth basically. So the depth will be depth and alongside the level, because level can be increased. And now what we'll be doing is checking for every child in node.children. And yes, I forgot to say this, that in binary search we have a left or right node, but in n-ary tree we have, not in a binary search, in a binary tree we have a left and right children, but in the n-ary tree we have just a children list. So this is how we are going to do things like appending all of the children in uh, in a tuple form obviously. So children will have alongside level plus one, because whenever we go to the child and child of a child of a child, we are going deeper and want to increase our level plus one at each step. So what we'll be doing after that is just return the depth. So this looks good. Let's see if this works or not. This works, and let's submit it. Okay, so this was our depth first search, so in which we used our stack and did things with the stack. So this is, let me just copy it, and that's it. Now we will be doing things with breadth first search. So, okay. So how breadth first search works is just level by level. This was just using a stack appending, going down to the very left, you can say, and then going down deeper and deeper in depth first search, top to bottom approach. And this is just depth breadth first search is just right to left or level by level, you can say, a traversal. So what we'll be doing is making a queue, and if the root is valid, then we will just append it to our queue. So queue, oh, dot append with, again, with a tuple alongside the level, which will be 1. And now we will be making our depth. So this part is the similar. So the every node alongside its level, so every node alongside its level, which is just our tuple in queue, what we want to do is just update our depth by the certain level. And for every child, of a node children children, what we want to do is uh, append it to our queue. So queue, q u q, what was the spelling of q? Okay, so q dot append alongside the child itself and the level plus 1. And after doing that, we can just return the depth and that's it. Let's see if this works, and then I will explain how these two both algorithms are working step by step. So this works, and let's submit it. So we are going through every list, every node. So this is an O of n, both are O of n. So first we will be taking a look at the stack, or stack, I said, the depth first search stack solution. So first of all, we will be making a stack. Just for explanation, this is just explanation, the code is done. And the depth, we have a variable depth which will be equal to 0. So we do have something in our root, because we are passed down some root. Then what we'll be doing is just appending it to our stack. Now we want to see if there is something in our stack here. Yeah, there is something in our stack. What we want to do is just pop that tuple. So this was a tuple. I didn't use parentheses, just like these are in the form of like a pair, you can say. So the tuple has a node and the levels, a node and its level. So it is popped. Now we can just update our maximum, because we have a level 1. And now for every children of 1, we will append it to our stack. So 2 has the level of 2, because the previous level was 1 and it is being incremented by 1. So 2 2, 3 by 2, 4 by 2, and 5 by 2. Now we will pop from the stack, and this is how pop in the stack works. It removes the last element. So 5 2 is removed, and now we will append it with but before that we want to update our depth, so depth is increased by again the maximum level was 2, depth is being increased. And now for every child, yes, for every children we will we will add the children of 5, which are 9 and 10, and the level of 5 was 2, so the 9 and 10 will have the level 3, one increase, like uh, here level plus 1. So this is how things works. So the level is 3, 10th level is 3. Again looping again while the stack is not empty. Yes, it is not empty. Popping this does not have a, you can say, uh, a child node. 10 does not have a child node, so what we'll be doing is the depth will be increased by 3. And now what we'll be doing is again looping, and again what we'll be doing is just popping the 9, but and increasing our depth, but the level was same. 10 and 9 are on the same level, so the maximum will be the same. And now appending with our 13 and 4, so 13 is on the fourth level because the 9 is its parent and the parent level was 3, so the one increase. And now we see that 13 does not have its own left or right, not left or right, a children basically. So we will be just popping it, and now we have 4 2, we will just pop it, so we have a node reference and a level. And again appending 8 by 3. And now again looping, and because 8 by 3 is are on the same level, so 13 was, yes, I forgot to update my maximum in a hurry to just pop it, but the depth is being increased when it was on 13, so 13 has the level 4. So at in a previous step, like before 8, the depth was increased. So now 8383 is popped, and now we have 12 and 4, so it does not have a child node, so we will be just popping it again. Now we are at 3 at level 2. So now what we'll be doing is just popping 3, and it's this tuple, and we have a level, we have a node, we will be going down and just appending. And also the maximum is not going to be updated because it is 4 is just the maximum, the level is 2, so we are coming back, you can say, the like backtracking up. So that's it. And now what we'll be doing is just appending 6 with the levels 3 and 7 with the level 3, popping 7. And now we have a 7 reference, adding its child, 11 by 4, level 4, popping this because uh, taking the tuple and popping this. Now we have 14 with the level 5 because the children of that 11 was added appended in our stack, and now the level is being increased by 5. Now when we pop this, we are going to you can say increment, not increment, but take the maximum to our depth. So the depth is being increased by 5, as you can see here. And now what we'll be doing, like 63 does not have its children, so we'll be popping it. 22 does not have its children, we'll be popping it. Maximum depth is not affected, so the stack is empty, we are done. We will be just making out of the loop and returning the depth. So this is how the depth first search worked in this solution, and this will be the BFS, the breadth first search, BFS. Okay. So now what we will be doing, just making a queue, like just for explanation. So this is our queue, this is our depth, and yes, depth is 0, queue is empty. There the root was valid, root was not null. We will be appending the root, so the root was 1 and 1 as a tuple. So these are tuple, I didn't just use the parenthesis for, I don't know why, I didn't like to use parentheses here for just for explanation, otherwise it will give an error if we actually use them in the code. But let's get started now for the breadth first search appended to our queue. Now for every node in for every tuple in queue, so the first tuple in queue, what we want to do is update our length with level. So the level was 1, and now we want to add its children, so the 2 level is increased. Like this is just the same but with a queue and a level by level approach. So 4 2 4 2 and 5 5 2, yes, 5 2. Now this is done, 1 1 we have traversed. Now the queue is not empty, the queue does have 2 2, so we will be appending the children of 2 2. 2 2 does not have any children, so 2 is just basically the node, and 2 on the other hand is just basically the level. So that's it. And 3, if you see that 3 does have its left and basically children, left and right, yes you can say, but I am trying to avoid the left and right because these are just used for binary tree, and this is an n-ary tree, so we'll be using a children word which is more, you can say, specific to n-ary tree. And 6 with the level of what was the level 3, because its parent level was 2. So now what we'll be doing is 7 by 3. Yeah, 7 by 3. And now what we'll be doing is just checking the next node. So 4 by 2, 4 and 2, so 4 has its 8, 8 by 3. And now what we'll be doing is just it's the turn of 5, so let's make a pointer so it can be more easier. So let's say this C is our current pointer. Yes, okay, we are done here. We are just going to our whole queue, traversing through the whole queue. So these are, again I am saying, these are in the pair of like tuples. These are like let me just, these are in the form of like this, in the form of tuples. So I just didn't make it, I don't know why. So now we are at 8 3, 8 3, yes, 8 3. Now we are at 5, so now we will update our pointer to 5 which was already there. So now we will add like 9 with the level of 3 because it's the level of its parents was 2 and we added 1 to it. Now the level becomes 3. Again with 10 and 3, 10 does have 10 will be 3, like it is the, you can say, a brother of 9. They are on the same level, so it will have the same level. Now the pointer is being updated to 6, and now we have no children of 6, nothing is being appended. 7, 7 has an 11, so 11 will be appended by 11, 11 will be appended and the level is being increased. Again the pointer is increased again, and now there is no pointer. By the way, this is just, we are keeping track of things like 8, and 8 does have a 12 with, again the level is being increased by 1, and now we are traversing to 9, and 9 does have a 13, so we'll be adding 13 to our queue. And this is a queue. I Yes, we are using a queue. I think I said stack many times while explaining this solution, but this is a queue. And now what we'll be doing is just going to the 10. 10 does have, no, 10 does not have its own children, so appending nothing. And while we are doing all of this, the length of the length which will be the second portion is being increased. So far we have increased our length to 4, so the depth will be 4 so far. And now what we'll be doing, this was just going step by step. So at first it was 2, then when we reached here, like at the sixth portion, at the sixth, like when the pointer was here, I just forgot to just do it simultaneously. I was so focused on the queue, so it was like 3, and then it became, at 11 it became 4, and now it is still not the max. So we are at 11, I think we are at 11. Yes, we already traversed that. Yes, we are at 11. What we will be seeing is at 11 we have a children node which will be 14 with the level of 5 because its parents level was 4, and now it is being, the depth is being incremented because the depth is equal to the level, and level is 5. And now the 12 has nothing in its, you can say, as a children. 13 has nothing as a children. 14 has nothing as a child, or the level is still not going to beat the level we have already in our depth. And this is how we are going to just return the depth because we already traversed to the whole queue for every character, for every tuple in queue. So this is will be going out of bounds, and then we are done. So that's it. This is how you do depth first search and breadth first search in an array tree. And if you have any kind of questions, you can ask them in the comments. That's it.